Okay, so the topic of this talk is the top 20 secure PLC coding practices with CODESYS. So motivation behind all this. Just in general, we're seeing a very large increase in cybersecurity threats to PLCs as they become more connected. So it used to be that PLCs are very isolated. You didn't really have to think about security that much for PLCs, but that is simply not the case anymore. The big clear examples here is the Stuxnet virus discovered back in 2010. It destroyed over 1,000 centrifuges at an Iranian nuclear enrichment facility, jumping a complete air gap with a USB stick. So those PLCs were not on the internet. The attackers were just sophisticated enough to jump that air gap. And then more recently, the Triton malware discovered in 2017, targeting a safety PLC. Thankfully, the attacker's code had some bugs in it that actually did not do what they wanted to do. It just caused a shutdown of the petrochemical plant. But obviously, the fact that they were very specifically targeting a safety PLC means they were trying to cause physical harm with a cyber attack. And with the constant drive for more efficiency, with Internet of Things and more data analytics, and the PLCs and the control system networks being more and more connected, these threats are not going to go away anytime soon. They're only going to get worse and more important to address. Comparing the PLC programming world to the kind of normal IT programming world, computer programming has some pretty well-established guidelines for secure coding to help mitigate vulnerabilities and produce more reliable software. Some examples of these are the software development lifecycle, OWASP, secure coding practices for web applications. There's secure coding guidelines for Java, published by Oracle, and there's also the Microsoft development security development lifecycle. So we have all these guidelines and stuff for normal computer programming. There are always new vulnerabilities in regular computer programming, but these guidelines and frameworks help us reduce the chances of having vulnerabilities in our code and just making the code a lot more reliable. But the PLC programming world up to this point has lacked kind of similar standards. Everyone has kind of been doing their own thing, maybe sharing practices like Russ. That was a great talk on object-oriented programming. We're actually going to cover that just very briefly in this, but that is one way to help write more secure code. And so this whole effort that came out last year was trying to address this issue, trying to provide PLC programmers with just some kind of reference to try to write their PLC programs and configurations a little more securely. So this actually kind of got started at the S4 conference. This is an industrial control system cybersecurity conference a few years ago. A presenter just shared his kind of informal tips that he had collected over the years, being a system integrator, writing PLC programs, things that he had done to add security to PLCs. And then inspired by this, some organizers came together to actually formalize this into a top 20 list. So a consulting company called Admiritia, led by Vivek Panada and Sarah Flukes, as well as the organizer for the S4 conference, Dale Peterson, and then a bunch of other volunteers jumped on to help provide their feedback and things they've been doing and providing security for the PLCs. These were published in June 2021, so it is pretty new out there. And the official title is the Top 20 Secure PLC Coding Practices. And so we're going to go through each of these practices in this talk, showing you some screenshots of how I implement them in CODESYS. Don't have time to go into the details of all of them because it is a lot to go through. There's 20 different practices. So some I'm going to skip through faster than others. Some are pretty high level strategies. Others are very, very specific. And we'll kind of go through those as we get there. The practices are technically copyrighted, but the copyright is pretty liberal. You can use it however you want, just providing attribution to the original authors of the practices. So there's that license there for you. And as we go through each of these practices, they're going to be mainly trying to achieve one of 4 different security objectives. So integrity, covered by practices 1 through 12, hardening, covered by practices 13 and 14, resilience, covered by 15 and 7, and monitoring, covered by 16 through 20. So when we're talking about integrity, we're talking about detecting or preventing unauthorized changes, either to the program, the variables, or the IO values. When we're talking about hardening, we're talking about trying to make the initial compromise for the attacker more difficult, making it harder for the attacker to gain access to the PLC. Resilience refers to, we're kind of assuming some kind of compromise and we're trying to mitigate the threat to the PLC, continuing to provide, keep lights on, keep operations running, to keep everything running safely. And finally, monitoring is focused on trying to detect the incident as soon as possible to mitigate the damage. For each practice, we also try to cover the different benefits that they can provide to the PLC programmers and the operators. So not just security. I'm a security person, so I care a lot about mitigating threats from intentional attackers. But there's also other side benefits. So reliability, mitigating the threat from just accidents. You aren't attacked by nation-state level adversaries very often, but people do make mistakes pretty often. That's honestly the more likely scenario is someone programming the wrong PLC, someone just making mistakes. And so these practices help detecting and mitigating the threat from those as well. And finally, maintenance, making the code just easier to debug and maintain over the decades-long life cycle of the system. Each practice is kind of inspired and has references to a bunch of different frameworks and standards and guidelines you can read for more details. So these include the MITRE ATT&CK framework for ICS. This is just some formal descriptions of attacks on ICS and how defenders can mitigate against them. This goes into different tactics, techniques, and procedures the attackers use to achieve some kind of malicious goal on the control system. Also, a lot of references to the ISA 62443 standards, the substandards 3-3 focusing on system security requirements and security levels, 4-1 for secure product development lifecycle requirements, and 4-2 for technical security requirements for IACS components. And finally, we also provide a lot of references to the MITRE CWE or common weakness enumeration, just listing the common kinds of vulnerabilities that occur in software and how to address them. And finally, just kind of a caveat on the limitations here. Secure PLC grant practices are a great first step, but they are only one layer of defense. So this is not a replacement to good network security and monitoring. So you still need a good security architecture and monitoring in place. The unfortunate truth is that most PLCs out there are still insecure by design, especially the older legacy PLCs, meaning that anyone on the network, if they have even just a moderate amount of skill, can send a command to the PLC, cause it to do something bad, either or potentially reprogram the PLC, and that's just the design of the software and how PLCs are made. So these practices, these top 20 secure PLC coding practices, only make it harder for the attacker, just kind of increasing the level of difficulty to cause problems, but not impossible. So they're not a complete foolproof solution for securing the PLCs. Many can be worked around by the attacker if they have complete control of the PLC, which is not very hard in most cases. And monitoring is only useful if someone's actually watching it or they're getting active alerts and they know how to respond to it. And finally, These practices are only a first pass, and so the organizing committee is still looking for user feedback and refinement. So especially from end users who are actually out there programming PLCs, we're still looking for more feedback and improving and refining the different practices. All right, so finally getting started. Looking at the first practice. The first practice is modularizing PLC code. So a great intro, the previous presentation by Russ. Looking at object-oriented practices for PLC programming. This is kind of basically the same thing. Excuse me. For this, we're breaking down PLC logic into function blocks or subroutines, primarily trying to make them reusable, testable, and independent. So that for each function block or subroutine, you can really thoroughly test. You can focus in on that function block or subroutine, test the range of inputs, and all the corner cases of the different potential bad values might be coming in, and make sure your code handles it safely and in a predictable way. When you break down the code like this, it also makes it easier to record execution times, the size of each function block or package or whatever, in kilobytes. You can also maybe get some checksums or signatures for each block, and then track changes over time to detect when it hasn't changed, either from malicious or accidental changes. Another option that CODESYS actually does provide is you can lock each function block or a program with passwords or certificates, and so that does add a lot more security. It does also add a lot more work to the operators and end users. So, take that. If it makes sense, definitely try to do it. That is the best for locking those down. And so for this practice, it is addressing the integrity of the PLC logic. So, helping to detect and prevent changes to the logic itself. The side benefits of this, first looking at security, of course, helping to detect new code and modifications, to even prevent modifications if it is locked with a password or certificate. For reliability, it helps avoid program flow problems and also helping to avoid just accidental unauthorized changes. And for maintenance, it helps make the code a lot easier to read, having it separated into those. So you can go through, have a function block for just a general turbine that fits the requirements for that turbine. And then you can instantiate it for each of the actual physical turbines. And you can even go deeper, as the previous presentation illustrated, just breaking that down into smaller pieces, smaller function blocks, maybe for each step of the startup sequence. And you can very thoroughly test each step of the sequence. You can then thoroughly test that single function block for that turbine, and be really sure that you handled all those corner cases really well, and make it a little bit harder for attackers to manipulate that and cause problems. The next practice is track operating modes. So most PLCs have run and program modes, and they can only be programmed with the normal engineering software while they are in the program mode. So the general recommendations here are keep PLCs in run mode as much as possible, because if they're left in program mode, that just makes it way easier for attackers to reprogram them and cause problems. It's also really helpful to display the current mode on the HMI and alarm on when that mode changes. And that's really important because depending on the configuration of the PLC, depending on the exact PLC software, once the PLC stops, the values are not being updated anymore on the HMI. And so it may look like it's still running. And so it's really helpful to have that alarm kind of triggered event to raise that alarm when the mode changes. The exception here, of course, is if you have extended maintenance windows, you don't need to continue alarming that it's in program mode, but just make sure you take extra precautions to lock down the PLC programming, so it's not just wide open for attackers to modify. The benefits for this practice for security, it makes it significantly harder for attackers to modify the PLC. For reliability, again, kind of from an accidental change perspective, it makes it harder for just accidental changes to happen. And for maintenance, it helps a lot with change management. So you're getting very clear logs on when was this PLC modified, and kind of helping to track the changes over time. For the example, looking at what CODESYS provides. So if you go into the online menu at the very top, you can see operating mode. There's 3 different modes. There's debug, locked, and operational. Debug is the default mode, just what you do all the programming in. Locked and operational kind of prevents, there's slight differences there, but they both kind of just prevent changes to the program. So kind of making it in an operational state, it's locked down and doesn't allow changes to the program. There's also different modes between stop and run. So under the debug option in the top menu, you can either stop or start the PLC program. And so that's another way of controlling the mode. And then to monitor that. So say you're doing a good job, you're keeping it in the locked or operational operating mode. To monitor that, you first can add the library for CMP app under syslibs under system. So add that library using the library manager. And then you can use that to call some function blocks to get useful information about the operating state and the application state. So you first have to get a handle to the application by calling the name. Once you get that handle to the application structure, then you can just read the different values in that application structure. And some of those values are op state, UDI op state, and UDI state for the operating state and the application state. And those are just integers that refer to different kinds of states. And you can see that some of the documentation here, what each of those different values mean. So you can see the operating state can be anywhere from program operating state download, online change, forced active, exception. So very detailed different states of the program, and very useful to log what the current state is and when it changes, to know if the program has changed or if someone has any forced values on the PLC. And in a similar way, the application state, whether it's currently in stop mode or run mode or debug mode. Again, that key point of depending on how it's configured, depending on the PLC, the IO values may not update when the program is in stop mode. So it may look like it's still in run mode if you're just monitoring that value. So it's also really helpful to add an event handler to run some code to raise some alarm when the PLC does change to stop mode. So for CODESYS, you can look at the task configuration page under system events and add an event handler for the stop done event, such as saying that when the PLC program stops, run this function or application or POU to do whatever you want to raise that alarm when it stops. Moving on to practice number 3, which is weave operational logic in the PLC. So some HMIs have pretty high level programmability, and so it may be tempting to add a lot of logic to the HMI itself, but just make sure the logic you're adding to the HMI is not key to the safety and key to the operation of the physical process, because the HMI is more likely to be compromised than the PLC itself. And having the key safety features, the key operational logic in the PLC makes it harder for the attacker to compromise that. And so specifically, some of the things that are maybe tempting to put on the HMI is like summarizing and totaling logic, logic to enable and disable different buttons, and thresholds to trigger alarms. So all those are sometimes put on the HMI, but putting them in the PLC does make it a little harder for attackers to mess with. The security benefits to this approach, again, just making it harder for the attacker to manipulate things. So that especially in the case of if you have some kind of like single centralized HMI talking to a bunch of different PLCs. If it was all in the HMI, that's only a single target that the attacker has to compromise. Whereas if the logic is spread out in the PLCs, that means the attacker has to compromise all the PLCs to really achieve some kind of physical impact to the process. And a lot of times the security and access control on the HMI itself is not great. And so this prevents the attacker from just bypassing the HMI logic to operate the PLC. And so the checks are actually happening on the PLC itself. They can't just send the Modbus command directly to the PLC to cause some problems. For reliability, this helps with calculations being actually more accurate the closer they are to the source. And for maintenance, it provides a better separation of change management. So keeping the change management and just the PLC logic all in the same place instead of being split between the HMI and the PLC. The next practice is using PLC flags as integrity checks. So most PLCs in CODESYS has different log faults and flags for various error conditions. So for example, divide by 0, like a math error, counter overflow, negative counter timer presets, or some overrun flags and issues. So this practice is all about just adding counters, making sure you're tracking all those flags and errors, and making it so you can investigate them later. So not just ignoring them, not just handling them and assuming that everything's okay. Making sure you actually log that so you can investigate it later to verify whether maybe you need to update your code to handle some weird condition better, or maybe it's some kind of malicious manipulation happening that you need to investigate and address. The security benefits here, it helps to detect some specific malicious manipulations and some poorly written modifications. For reliability, it does help maybe provide better graceful handling of errors, not just letting those errors accumulate and maybe cause problems. For maintenance, it does help provide better debugging of errors. Having very clear logs of all those errors happening makes it a lot easier to debug over time. For CODESYS, the main way to do this, the easiest way to do that is looking at the device logs. So all the different informational error and exceptions are all stored in the device log, all timestamped and related to the exact component. So here's an example. You can see there's a divide by 0 exception in the My App application in the main task. So it's a very clear logs about where the exception happened, so you can go investigate, what happened, and maybe update your code. The next practice is using cryptographic checks or cryptographic hashes or checksums as integrity checks for the PLC program. So different PLCs offer different things. They're all kind of given the same idea of methods for fingerprinting what the PLC program is and what the configuration is, and using that to quickly identify whether the PLC program has changed or not. There's a few different ways of doing this. PLCs range from using audit values or checksums or actual cryptographic signatures. CODESYS has a lot of different options here. And so what you want to do is log this as part of maybe the site acceptance testing when the program is actually deployed on site, saying this is the final production fingerprint of the PLC program, and this is the gold version. And in the future, you want to alarm when that changes and just document each major version is like, you have that hash or that checksum to identify what that version was. Security benefits here, obviously detecting malicious changes to the program. So when that value changes, that detects change to the program. Reliability helps to detect just accidental changes. And maintenance, just having more information and better change management logging. so having the fingerprints of each major version of the PLC program. So CODESYS offers a couple of different ways of doing this. One is for every package in CODESYS, they have a checksum so you can verify that the package has not changed, or you just know that it's the right version of the package. The other way, the more secure way and complete way of doing this is using the certificate. So there's a whole walkthrough. I did not have time to go through. The link here is the CODESYS documentation for encrypting and signing project files and boot applications with certificates. But the kind of short answer here is that using strong cryptography, you can actually provide digital signatures and encryption to really verify that one, the program has not been changed, and two, it was authored by someone you know and trust. That's the whole concept of a digital signature. It's signed by someone you know and trust, and you verify that it came from them using this method. So that is definitely the most secure way of doing it, and CODESYS does allow you to do that using that walkthrough. The next practice is validating timers and counters. Sometimes timer and counter preset values aren't hard-coded. Maybe they're coming from the HMI, maybe they're coming from internal logic and calculations. And so it can be good and helpful to have an extra check to make sure that that preset value is valid or safe. Even if it is preset, even if the preset is hard-coded, having an extra check in there does make it slightly harder for the attacker, meaning they have to modify 2 places in the logic to maybe cause problems instead of just the one. For security benefits, this helps prevent some manipulation from the HMI and network, making it slightly harder for the attacker. For reliability, it helps prevent accidental bad preset values by having those double checks in there for the valid ranges. And for maintenance, it helps provide better documentation of valid values as the program gets updated, having that clear documentation of what a valid preset value is. And so a very simple example of how you might do this in CODESYS. So I have a timer block up there in the top, and just have a double check to see if what the preset value is for the timer to verify whether or not it was the exact time that we set. So it looks here like the timer block has a preset value of 3 seconds, but our check has a preset value of 5 seconds. And so you might want to raise an alarm to say that double check that the preset value was wrong. Maybe someone modified it and they didn't update it in both places. If that's the attacker just trying to play around with the code and mess with something, it might help them check. The more complicated case of the preset values coming from some other calculation can also provide some double checks of whether or not the value is right. And in a similar way, we have some kind of counter block counting something on the production line, and we want to verify the preset value that it's supposed to be counting up to has not been modified. We can have an extra check for the preset value equaling 12. And in this case, again, it looks like someone's modified it. It's not the right preset value. And so we could raise an alarm on that difference. Looking at practice number 7, validating and alerting for paired I/O. So what we mean by paired I/O is I/O that physically cannot happen at the same time. Something cannot be physically starting and stopping at the same time in forward or reverse mode or open or close at the same exact time. So if the variables are active at the same time, it's either a malicious attack, the attacker's just kind of blindly messing with things, or potentially a logic problem. And so the motivation for this is that one of the easiest attacks that a attacker can try to do is just rapidly toggle all kinds of variables from the network without really doing any research on what they represent. And so it makes it a little bit harder for the attacker if the paired I/O are separate variables and you have logic in place to to ensure that both outputs are not asserted together and alarmed if they are asserted together. Another kind of variation on this, something else you can add is adding delay timers on I/O if rapid toggling can cause damage. So a motor starting and stopping very rapidly maybe can wear out the motor faster, and so maybe you want to add a delay timer to just make sure that it does not get toggled too rapidly to cause any problems. For security, this helps prevent some malicious network attacks. For reliability, it helps prevent just accidental rapid toggling. So some logic is written poorly in the HMI, or maybe just a faulty wiring is happening that would cause rapid toggling. So having that kind of debounce, having that delay within the PLC logic can help maybe detect and prevent physical damage from happening, that rapid toggling. So looking at a simple example here in CODESYS, maybe we have a forward and reverse variable. And so when the state is in the forward mode, you execute some logic for forward, and then in reverse, you have some different logic you execute. And so you can just add some checks there that if the forward and reverse variables are both active at the same time, then you raise an alarm saying, hey, that's, it shouldn't be like that. Something's wrong here. The next practice is validating HMI inputs at the PLC itself. So values should be limited to safe ranges, not just at the HMI, but also in the PLC logic. So it's good, and you should limit the values to safe ranges at the HMI so you don't accidentally try to set something to bad value. But most control system protocols are not authenticated, and so an attacker can just send a command over the network, bypass the HMI, to write the Modbus register, to write an ENIP variable to cause some problems. And so having actual safe checks within the PLC itself helps prevent those issues. And you can approach this a couple of different ways. If an invalid value is received in the PLC, first of all, you do want to log it just to know and keep a record of, hey, we got a bad value here. We don't know if it's an accident or an attack, but just logging it can help with investigation to figure that out. And when you get that value, you can either choose to maybe use some default safe value, maybe use the last valid value that you did receive, or maybe limit it to the closest max or min within the safe range. For security, this helps prevent malicious manipulation from the network. For reliability, it helps prevent just accidental input of unsafe values. And for the example looking at CODESYS, in this case, we just use a simple limit function block, so that kind of clamps down the value to some specified max and min safe range. So we have some HMI variable coming in, we have some lower and upper safe limits, and then the physical output is limited to those safe max and min values. Then you can also add some checks to see if if the HMI variable is above the upper safe limit, so that means somebody from the HMI or just from the network tried to write a value that was too big, then we want to maybe use that default value or use a safe value and raise an alarm saying that we received an invalid HMI value. Practice number 9 is validating indirections. And so indirections, what we mean here is using one value, using the value of one register in another register. The most common use case here is lookup tables or arrays with a variable as the index. And so if the indirection uses the wrong value, you could either overwrite important tags, or you could execute wrong logic, or you could try to read out of bounds of the array and cause problems. So The easiest way to do this is just add checks for out of bounds index before you access the array. Another kind of more complicated approach, you can look at the document, the top 20 secure PLC document, but you can do something with poisoning array values and just using that to help monitor for accidental overrides of poison values. But you can also just check for out of bounds indexing. So this, for security, makes it just harder to manipulate the logic. The attacker has to really understand your program to cause problems. For reliability, it helps prevent programming errors. If you didn't write the logic quite right, it helps prevent and detect when those indirections might be going wrong. And looking at an example in CODESYS, how you might do this. So you just have some checking of ranges of if the motor index is greater than 0 and less than 11, then it is a good index. Then only if it is a good index, then use that lookup table for that motor index to update the motor speed. And so ladder logic is kind of more complicated in this example. Using structured text would make this a little bit easier to implement. But just the concept of before you use the variable from the array, just do some checks on whether it is in a valid range or not. And if it ever is not in the valid range, you want to raise that alarm and log it. Practice number 10 is assigning register blocks by function. So this one, so the practices were written to be generic to any PLC. And so some apply more to legacy PLCs versus more modern PLCs for very specific scenarios. So this one doesn't apply as much to CODESYS PLCs, but the idea here is that grouping variables and registers by function, whether they're read-only, writable, or local, makes it easier for firewalls or intrusion detection systems to either block writes or reads to different ranges of addresses or detect that, and just limit what is writable from the network. And so really the only application here to CODESYS is maybe if you have a Modbus server grouping the different ranges of what your Modbus register numbers are, and grouping them together functionally so that if you are monitoring from the network or if you have a firewall, you can use the register numbers to detect when reads or writes are happening to different sensitive areas of the Modbus address range. For security, this just helps reduce the attack surface from the network. So really locking down what the attacker can do from the network. For reliability, it might help prevent problems from just accidental writes to the wrong address. And for maintenance, it just helps make sure you have better documentation of what all of your network variables are and what the valid ranges and everything are for those values. Practice number 11 is instrumenting for plausibility checks. So the idea behind this is cross-check multiple sources of sensor data for related plausibility. So some examples here could be comparing the integrated or summed measurements with the instantaneous values. So imagine if you have sensors for flow rate in a pipe, and then you also have a sensor for the tank level or the volume of the tank that it's flowing into. You can be integrating the total amount that has flowed through the flow sensor and comparing that with the level of the tank and calculating what the volume of the tank is. And so is there a major discrepancy there between the two sensors? Another approach is, for example, if the burner is on, the temperature should be increasing. Just having a check in there, just do things seem to be behaving like they should? If the burner's on, the temperature should be increasing. If it's not increasing, then maybe something, maybe the burner is not actually heating things up. Maybe you have some other problems. Maybe an attacker is injecting false data into the control system. And other approaches are just comparing different sensors that should be related. So looking at, if the valve is open, then the flow rate should be greater than 0. It could be a simple check. Or if the valve's closed, the flow rate going through that valve should be 0. For security, this makes it a lot harder for the attacker to manipulate all the sensors. With these checks in place, they can't just manipulate one sensor to try to cause a problem, because your code should be cross-checking all those different related sensors and be able to detect the problem. So in order to go undetected, the attacker has to manipulate all the sensors in a way that makes physical sense, that bypasses your plausibility checks. For reliability, this helps you to detect corrupted or wrong sensor values. And for maintenance, it helps you just debug things a lot faster, having those plausibility checks in place. So an example in CODESYS, I've implemented here just kind of like a pulse that happens every 1 second, and we're using that pulse to add up how much flow is currently going through this flow sensor. So when we see that pulse, we add the current liters per second into some totalized volume variable. We then compare the difference between the totalized volume and what the tank volume sensor is telling us. And if the absolute value of that difference is ever over some threshold, then we say, hey, there's a major discrepancy here in what the tank sensor is saying and what has gone through our volume, gone through our flow sensor. So something, maybe one of the sensors is failing or wrong, or maybe an attacker is injecting false data into the system. Practice number 12 is validating inputs for physical plausibility. So kind of similar to the last one, but in this case, we're focusing on only allowing inputs that are physically possible or safe. So this one kind of addresses a little bit of what happened to the old SMAR water utility, where the attacker gained access to the HMI and tried to set the levels of sodium hydroxide to some ridiculously unsafe level. And so these kinds of practices are just making sure you put in checks to make sure that's just not possible. The attacker can't try to set those values to unsafe levels. Different variations on this. You can also add maybe a timer for longer operations to verify that it does complete in some physically plausible amount of time. So maybe you have a big valve that takes a few seconds to fully open or close. And so you can actually time that operation and detect whether if it took too long, maybe it's stuck, or maybe something's not working right. Or if it happened too quickly, either that's false sensor data, maybe some wiring is wrong, or an attacker is injecting false data to say that it did successfully close or open when it did not. Another variation on this is monitoring kind of like a heartbeat of expected regular operations. So if you know that something is supposed to pass the assembly line every few seconds, or some operation is supposed to happen, some batch process is supposed to happen every few hours, just time that and see if it's within some reasonable range. For security, the benefits are detecting false data or actuator tampering. For reliability, it's helping to detect device or sensor failures. And looking at an example in CODESYS, we have some valve positions. And so we have the current valve position and the set valve position. And if that difference between those positions are non-zero, that means the valve is currently moving. And we have a timer here to monitor how long the valve is moving. And so in this kind of scenario, we're setting the control system is just setting the valve to a specified position. We're monitoring how long it takes to get to that position. And if it ever takes 3 seconds or longer, then this time block will enable this slow valve alarm. It'll just say, you know, the valve took at least 3 seconds to actually get to its correct position, and so something isn't quite right. The valve is taking too long to get to the set point. Number 13 is disable unneeded ports and protocols. And so PLCs, especially the newer ones, come with a lot of different protocols supported. Thankfully for CODESYS, this is not exactly the case. OPC UA, I think, comes supported or enabled by default. Everything else you kind of have to enable as you need. So there's the big idea here in general is disabling ports and protocols that are not needed to just reduce the amount of options the attacker has to try to attack. It's also helpful to develop data flow diagrams showing the required communication for PLCs and physical ports. Just how is the data flowing through the PLC, what protocols, what ports are flowing through, to really help you visualize and understand potentially where could an attacker gain access to the PLC and mess with variables. For security, this reduces the attack surface and the number of options the attacker has to get into the PLC. For reliability, it helps reduce unnecessary traffic. And for maintenance, it's just a lot easier to document and track changes if it's simpler. There's less things enabled on a PLC. And again, for CODESYS specifically, OPC UA is enabled by default. Disable it if you're not using it. Don't add protocols unless you really are using them. And on the host itself, you can also configure a host firewall to only allow the needed ports for CODESYS and whatever else you're using. Number 14, kind of related to that, is restricting third-party data interfaces. So this is just very dependent on your exact process and industry. Sometimes different organizations need to share data across their control systems directly into the control system. So for pipeline metering, for regional water producer and local utilities, they need to share data about flow rates and metering. Sometimes those are directly connected with the PLCs. And so the idea here is just restricting that communication as much as possible, really walking it down, really making it simple to track that communication between the other organizations. So having dedicated equipment and communications paths, using authenticated protocols if possible, using access control lists and firewalls if available, and only giving the other party read and write access to absolutely what they need, not anything else. So for security, this helps, again, just reduce the attack surface, reduce the options available for an attacker to cause problems, helps prevent some basic spoofing attacks. For reliability, it helps just prevent accidental changes that'll disrupt the process. And for maintenance, a simpler connection that's easier to document and keep track of over time. Number 15 is defining a safe process state for reboot. So PLCs can unexpectedly reboot, just an accidental loss of power, but also one of the easiest exploit attempts attackers can try is just kind of like brute force attacking the PLC, causing problems in the software, causing it to reboot. And so it's good to track when the PLC has rebooted, investigate, did you record a power outage just from normal problems, or was it potentially an exploit attempt on the PLC? And then when you do detect that, you want to be able to start the PLC back into some safe state. You don't want it just to pick up. You may or may not want it to pick back up where it left off. You may want to reset it back to a safe state, and so it doesn't cause any unexpected problems picking up in some kind of random state where it left off. For security, this helps possibly prevent physical consequences from an attack. So if they just do a brute force to cause it to reboot and you start up back into a safe state, then you've hopefully avoided any physical damage. Maybe you just caused some downtime, but you avoided some physical damage of it starting up in a state that causes problems. Reliability, this just helps really ensure you get safe reboots if you do accidentally lose power. Number 16 is summarizing cycle times and trending them on the HMI. So program execution times are usually available as some system variable in the PLC. And these times are relatively consistent. They're executing the same program over and over again, not many changes unless the program itself changes or unless the physical process significantly changes and executing new branches of code that it never did before. Or maybe if there's significant changes in the network, it might cause some timing issues in the PLC program. The idea here is monitoring potentially the average, the max, and the min scan cycle times, trending it on the HMI to visually detect it, and maybe setting some alarms to detect some obviously wrong or obviously bad cycle times. Kind of the limitation here is that you have to be visually monitoring things or having to very coarse-grained alarms to detect what happened. So it's nice to have automatic detection for when this changes. And this is actually what one of our products, Logic Watch Pro, does, is using machine learning to monitor these times and automatically detect when the execution time deviates significantly from the normal behavior and alert when that changes. For security, this helps to detect malicious program changes. And then for reliability, it helps to detect those accidental program changes. For CODESYS, one way to do this is using the CMP IEC task library. So you import that library from the library manager. Then you have to run a few different function blocks to get out that information. So you basically get a handle to the current running task. You then use the task get info function block on that handle to get information about the task. And some of the things you can get here are the last scan cycle time, the max cycle time, and the min cycle time. So you can use those values on the HMI, average them if you want, and just trend that to get an idea of what the normal behavior is for the program. Number 17 is logging uptime and trending it. So again, as I mentioned before, PLC reboots can either be a maintenance problem or an exploit attempt. So monitoring when the PLC reboots is important. You can either do that from the PLC logic itself, or if the PLC supports SNMP, you can also do that from the network. So for security, the benefits is detecting reboots can indicate potentially malicious actions. For reliability, it helps to detect just power loss reboots, investigate why that happened. Using CODESYS, one way to do this is importing the systime RTC or real-time clock library. You can read that with this function block systime RTC get. And then you can just kind of track when the PLC rebooted by having some kind of first scan bit where you read the current time and store that in some kind of last boot time variable that you display on the HMI to help log when the PLC is rebooted. Number 18, log hard stops and trend them. So hard stops from faults can indicate maintenance problems or attacks. So it's important to log all that for investigation before continuing operations. And it's really important to have accurate timestamps so it's easier to understand the sequence of events about what happened when. Security, this helps to detect some attacks. It's giving you more information investigating about what happened. And for reliability, this helps to detect programming issues and help you debug things faster when things do go wrong. And again, for CODESYS, you can use that device log to monitor all that. Number 19 is monitor memory usage and trend it. Important to keep in mind here, there's two types of memory, either just long-term storage or more dynamic RAM usage. different PLCs offer different ways of tracking that. A change in that memory can indicate a change in the program, meaning there's more or less running code. And so it's useful to track that and alert when that changes. So for security, this helps to detect some malicious changes. For reliability, it helps to detect maybe you've used up all the memory on the PLC, so helping to detect that when you do that by accident. Can be useful for maintenance, helping to tune the program and for troubleshooting when there's issues. For CODESYS, one way to do this is using the app get segment function block. So before you use that, you have to, and this is using the CMP app library, you have to first import that. Then you get the application by name, that handle, use that app get segment function block to get information about the different memory segments within CODESYS. In this case, I'm using the DA memory segment and just getting the size using from that move that move instruction. So just getting the size of the DA memory segment. You can track that in HMI and alert when that changes to maybe indicate a change in the program. Finally, number 20 is trap false negatives and false positives for critical alerts. So this is basically just adding double checks for very critical alert conditions. So checking for alarms when not firing when they should be, which is a false negative, or checking for alarms firing when they really should not be, for a false positive. So this just makes it just a little bit harder for the attacker to cause problems in the program. Yeah, and that's the main benefit here, just making it a little bit harder for the attacker to hide their attack. Having that double check in place means that they would have to change it in both places, not just one. So maybe you have a pressure alarm. If the pressure exceeds some value, then raise that alarm. And so you just have an extra check in there to raise to check if the alarm is not happening when it should. That's a false negative. Raise that alarm. If you're getting the alarm, having that double check in there to see if the process values are actually outside of the range or not, indicating a false positive if it really should not be alarming. So in conclusion, and the main takeaways here are threats to industrial control systems and specifically PLCs are definitely increasing. And we just provided a few ways the PLC programmers can add security by following secure practices. Kind of the high level things we covered were adding integrity, basically just don't trust anything from the network, add logic in the PLC to not just blindly trust everything from the network. Hardening the PLC by limiting the attack surface, just removing unnecessary functionality that might make it easier for an attacker to gain access to the PLC. Adding resilience to the PLC by assuming that things are going to go wrong, trying to fail safe, trying to mitigate damage to the process. And finally, adding monitoring, trending essentially the KPI of the PLC programming itself to help detect incidents in the control system. So if you want to learn more, reach out to me or the top 20 secure PLC coding practices group. We would still love to have your feedback. Like I said, they're trying to refine the practices. They want feedback from real users like yourself. So please do reach out to us if you have any questions or feedback. And with that, I'd like to thank everyone for the time and would be